Yeah, so after we finish solve our problem number 4, sort an array, and we did the efficiency analysis. All right, so the last small topic I want to talk about here, summary. Yeah, the summary about elimination method. Yeah. Because at this point, we apply this elimination method a few times. Yeah. For this class, this simple method is very important. And then later, in our homework assignments, exercises, we will have many questions we need to use this elimination method. So here I do a simple summary here. Yeah. All right. So very simple. The goal, why? So the main reason we applied the elimination method, reduce the problem size. Because after the elimination, your problem size becomes smaller. Yeah. So as a result, after you reduce the problem size, here we use this principle. Yeah. So this line, this statement, I treat it as a principle. So we use this principle. Yeah. So what's that? The smaller the problem size, the easier the problem. Yeah. Look at this statement. Yeah. It's pretty easy to understand. The larger the problem size, usually the harder the problem. Yeah. But here I want to make some comments on this statement. Yeah. I call it principle. I call it a principle. It's not a law. Okay? So we know there is a law. Sometimes people call law. Yeah. Here, this one is a principle. Yeah. So the main difference is when we say something is a principle, then usually we so our understanding on the principle is it may not be 100% correct. It mostly correct. Most of the time it is correct, but there is some exception. The principle, when we say principle, there is some exception. Yeah, for the exceptional case, it may not be correct. Okay? But if we say law, it must be 100% correct. No exception. It must be always correct. Yeah. All right. But in our problem solving, many times we use many principles. Many principles. So usually we use those principles as the guideline to help us solve the problem. Yeah. All right. Yeah. So that's the main reason we use those principles. Yeah. Here, this is the statement. We treat it as a principle. Yeah. All right. Then I want to explain the exception. Yeah, because here I didn't write principle. Yeah, here, let me put here. So we use this as a principle. All right. It's not a law. Okay. So this statement, it's not a law. Right. If it's a law, we mean it must be 100% correct. If it's a principle, 90-something correct, but there is some exception. Yeah. Here, let me talk about the exception. So that means this statement, sometimes it may not be correct. Yeah. So here, let me talk about exception. All right. Exception of this statement. So what's that? The smaller the problem size, the easier the problem. We can find a special case. sometimes a problem with smaller size could be harder than a problem with larger size. That could happen. Okay? Yeah, here. So this case very special, yeah, but it could happen. It could happen. All right, so here I want to show you a special example. This example, so that is a problem with a smaller size could be harder than a problem with larger size. Okay? Yeah. So this is a, exception of that principle. Yeah. Yeah. Although there is this exception, it does not mean this principle is useless. Okay? Yeah. Because it has, 90-something% correct. 90-something% correct. Yeah. That means this principle is still useful in our problem solving. Yeah. But we just need to be aware of the exceptional cases. Yeah. All right, so here, let me give you the concrete example here. Concrete example about this exception. First, I need to explain the concept problem size. What is the problem size? Yeah. At this point, we understand the problem size. Yeah, so here, we want to understand the concept of problem size. What do you mean the problem size? Yeah. All right. So our current problem size understanding, look here, the given array, the problem size is n. Here, the problem size, the number of elements in the array. Yeah. So our usual understanding, our, most of the time, our understanding, the number of elements in the array. All right, so that's our first problem size understanding. But there is another problem size understanding. Yeah. Yeah. It's also useful. Later, we have some special problems. We need to use our second problem size understanding. So what's that? Yeah. It's the magnitude of the number. Magnitude of the number of n, of the number n. Because here, this n, we use its magnitude. Okay? How large it is. Magnitude here, how large it is. The larger the value, the bigger the magnitude. That part. Not number of elements. Yeah. The element number only one. Yeah, because you only see one number. This n. That's the only number you see. Okay? One number. So here we do not use the number of elements. Only one number as our given data. But for some problem, we use its magnitude. Now here, let me give you an example for this case. Example for this second problem size, its meaning. Okay, all right. The example is here. example. Prime factorization of n. Consider this problem. So we want to do prime factorization of given positive integer n. Yeah. So prime, you know prime, right? Yeah. So the prime, yeah, let me list a few primes. 2, okay, 1 is not a prime. 2, the smallest one, 2. 3, 5, 7, 11, 13, 17, 19, and so on. Okay, so these numbers, here we are only look at the positive integers. These positive integers only have 2 different factors. Only 2 different factors. One factor is 1. Another is itself. Only these 2 factors. Okay? 2 factors. 2 different factors. These numbers we call prime. So here, the prime factorization, given any integer, positive integer n, we want to do prime factorization. In this problem, what's the problem size? The problem size, yeah, because here you're only given 1 number, right? 1 element. Yeah. But the value of this n, or the magnitude of this n, determines the difficulty of the problem. How hard is the problem? We need to look at its value. This number, the value of n. Sometimes it's hard, sometimes it's easy. Look at this problem. Okay? Yeah. For this problem, you can see this principle may not be true. Okay? The principle we are talking about here, not true. Yeah. Not true. Why not true? That is, sometimes a problem with smaller size could be harder than a problem with larger size. Yeah. So here I'll give you simple examples. Okay. Yeah. One is, look at the prime factorization of 1000. Yeah. That's the size. The magnitude of this number, 1000, that's the size. To do the prime factorization of this 1000, very simple, right? Very easy. Yeah. 2 cube times 5 cube equals 10 cube, right? Yeah. 2 cube times 5 cube, 10 cube. The factorization is very easy. Then, let me give you another question. N equals 357. The problem size smaller, right? Yeah. 357 is smaller than 1000. But if I ask you to do the prime factorization, is it much harder than factorizing 1000? Right? Yeah, because I need to do quite some work here. Okay? I need to do some integer divisions, several integer divisions, to check if there are several prime factors. Right? Yeah. Much harder than the one with larger problem size. Okay? Yeah. So this example, we can call a counter example for this statement, the statement given here. Okay? Yeah. Yeah. So that's the reason we call this statement principle. Not necessarily 100% correct, but it is still very useful in problem solving. Yeah. Because in problem solving, 90-something% correct, already very useful, can help us solve many questions. Okay? Yeah. For the exceptional cases, in case it's not correct, then we do not use this principle, right? Yeah. We can use other principles. Yeah. Where this statement is not correct, when we do prime factorizations, then we can change other principles to use, right? Yeah. Yeah. So here, I spent a lot of time. I try to explain, this understanding, this special understanding. Okay. All right. So that's the first statement. Second one, when some elements do not change the outcome. Yeah. So that's about the details of the elimination method. Yeah. If, based on the given information, after we do some analysis work, we find that some elements do not change the outcome. Yeah. So if we remove those elements, still you have the same outcome. Okay? Yeah. Then they can be eliminated from the consideration. Yeah. And after the elimination, your problem becomes easier to solve. Yeah, because you consider a smaller problem, and we know in principle it should be easier to solve. Okay? Yeah. All right. So that's the summary of this elimination method. Yeah. All right. So later I will show you many examples. So we try to practice this simple method many times. Yeah. All right, so next topic, 8.2, impact of organized data. Yeah. Here we need to solve another computing problem. Problem number 5, element uniqueness problem. Yeah. Here you can see we want to check if the given data, the given array, if the elements in a given array are unique or not. Uniqueness problem. Yeah. Given an array, yeah, how to check if all the elements are distinct. Yeah. All the elements are distinct. Yeah. If all the elements are distinct, then uniqueness, yeah. So it has the uniqueness property. So the checking function should return true, otherwise false. Right? Yeah. So very simple. Yeah. But here we know, although you can find a solution solving this problem, but you need to think about how to find an efficient solution. Yeah. If your solution is not efficient, you need to do some more work to find efficient solution. Yeah. All right, so here we want to compare two different methods. Yeah. All right. Method 1, method 2. Method 1, brute force method. Yeah. So we use the brute force method solving a few problems. Yeah. So let's solve this one using the brute force method. All right. Method 1. Yeah. We just do the comparison directly. So do nothing to organize data. Yeah. If you do some extra work to organize the data, yeah, so we may not treat it as the brute force method. Yeah. We just want to do the comparison immediately. Yeah. All right. Yeah. So that means we do not pay anything. Yeah, so there is no cost in organization, data organization step. Yeah, no cost. Yeah, for the first method. Our second method, we will pay some cost. Yeah, we will do some work to organize the data. Yeah. All right, so look at this array. How do you check there are at least two elements in the given array with the same value? Yeah. So we want to check that. Yeah. If all the elements have different values, so then the function, the checking function, returns true, distinct, true. Yeah. Otherwise, if we can find two elements, we only need to find two of the elements with the same value, then the function returns false. Yeah. All right. If we use the brute force method, yeah. First, let's consider if the first element is repeated anywhere in the remaining of the array, right? Yeah. So first we want to look at the first element. Is there any other element in the remaining part of the array has the same value as the first one? Yeah. If that happens, then the function returns false. Right? Yeah. So, yeah. So that's our, first round checking. Yeah. Because we need to compare, do comparison with, each of the elements in sequence, right? Yeah, one by one in sequence. Yeah. So that means for the worst case here, the parenthesis, number of comparisons we need to do for the worst case, that is n minus 1. Yeah. You need to do at the most n minus 1 comparisons. Yeah. For the best case, one comparison, right? Only one comparison. Yeah. For the worst case, n minus 1 comparison. Okay? Yeah. All right. After that, yeah, if we couldn't find two elements, yeah, in our first round checking, if we couldn't find any later element that equals the first element, then we need to do second round checking, right? The second round checking, we need to look at element with index 1, then do the comparison with the remaining elements, right? Yeah. So this time we need to do n minus 2 comparisons for the worst case. Yeah. For the best case, still one comparison. For the worst case, n minus 2 comparisons, and so on. Okay. So later, so we just keep doing things like this, and we need to. Yeah, we need the last one. We need to do the comparison, the element with n minus 2 index, yeah, and the one comparison. Okay, all right, yeah. This is the brute force method. In this brute force method, you can see it can solve the problem. Yeah, it can solve the problem. Yeah, and in this solution, we can look at its best case, worst case, average case efficiency, right? Yeah. Okay, no problem. Rohan, yeah, yeah. Just after the class, I just check your name after the class, yeah. Or in the break time. In the break time, I can check your name. Yeah. All right. Efficiency, the best case, easy, right? The best case, For the first element, one comparison. That's it, because the function returns false. We get the function value. Yeah. So the best case, one comparison. No more. Okay, just one comparison. Okay, yeah. All right. But the worst case, then each round comparisons, you get the worst case. Yeah. All right. Yeah. Here, I give you a special case. The last two elements have the same value. The last two elements have the same value. Yeah. Here, for simplicity, you can see these elements, their values are the same as their indexes. So here I choose, these numbers as simple as possible. Yeah. So the values. Yeah. For the last two, different indices but the same value. Yeah. All right. How many comparisons for the worst case? So we need to add up these n-1 consecutive numbers to get this 1/2 times n minus 1. So that's worst case. Yeah. The best case, the worst case. Yeah. All right. And you can calculate the average case, right? Yeah. Here, so you can calculate the average case. Not very hard. Yeah. All right. Yeah. And so here, I'll let you think about it. Okay. Think about it, the average case. Yeah. All right. Next, let's look at the second solution. Yeah. So we just did the first solution. The second solution, pay for some cost to organize data. Method number 2, investment in data structure. Yeah. Before we do the comparison, let us organize our data. But we need to pay some cost. Okay? It's not free. Okay? So we need to apply some comparisons. We need to do some work. Yeah. But that work, later, we will get payback. Yeah. Because the work we spend to organize the data is helpful. Yeah. So later, based on the work, after the data is organized, we can do much faster. Yeah. So that's the idea for the second method. Yeah. All right. How to organize the data? We do this kind of work. We sort the array first with certain cost. Yeah. We need to pay something. Yeah. We sort the array. We need to use certain number of comparisons to sort the given array. That's the cost. The number of comparisons we use to sort the given array, that's the initial cost. Yeah. Data preparation cost. Yeah. All right. So here, I want to use a relatively good sorting algorithm. Yeah. Not our first. Our first sorting algorithm, selection sort, that one, we need to use 1/2 times n minus 1. This many comparisons. Yeah. This algorithm is not good. It's not good. Yeah. Later, we can get many better algorithms. Yeah. So here, the one I select. So that is later, one of the better algorithms we will learn in our later classes. Okay. Yeah. But here I just use the result. Later I will show you how to get this n log n number of comparisons, okay, to sort a given array with n elements. Yeah. All right, so here, this is our data organization cost. Preparation, the first, the preparation cost, first step. Now, after that, after the data is sorted, then we can enjoy the good property of the data. Now the data becomes ordered. The original data is unordered, but after we sort it, we make it ordered. So next, when we do the checking, when we do the element uniqueness checking, we work on an ordered array. When we work on an ordered array, we can do much faster than before, right? So that's the idea. So that's the main point. Here, the question, how to check if any element is repeated in an ordered array. Now, you know your data is an ordered array. You can take advantage of this property. So when you do comparisons, you assume the array is already ordered. When you do comparisons, you should take advantage of this nice property to save many comparisons. All right, so let's do the comparison. This time, this array is in ascending order. Ascending order. All right. Next, let's do comparison. All right. So here, let me ask you, think about our goal. We want to check if there are two elements in the array with the same value. We just want to check that. Okay. Now, can you tell me how many comparisons we need to find if there are two elements in the given array with the same value? Can you see that? Yeah. Ascending order, already ordered. Yeah. So under this assumption, now you need to use the minimum number of comparisons to find if there are two elements with the same value. Can you see that? Yeah. Think about. Yeah. This time, you need to observe some critical property. The property is very simple. But you need to get it first. You need to get that critical property first. Otherwise, you cannot improve our, previous algorithm. Yeah. All right, so here, this assumption is important. Ascending order, increasing. Yeah. Their values are increasing. This property is important. All right. Now, let me point it out, the critical property. Yeah. All right. If there are two elements with the same value, so we make this assumption. Let me put this assumption here. If there are two elements with the same value, then the conclusion, that's important. The conclusion, then there must be two adjacent elements with the same value. Can you see that? Yeah. If there are two elements in the original array with the same value, because after sorting, do you put all the elements with the same value back to back in consecutive locations, right? Think about, if you have a few elements in the original array with the same value, after sorting, you will put all the elements with the same value in consecutive locations, right? There must be at least two adjacent elements with the same value, right? Yeah, that observation. That's the critical property. All right? Yeah, that's simple. Okay? Then, next, our algorithm will be based on this property, this critical property. Now let me ask you the previous question again. With this property, so this time when you do the checking, you only need to check two adjacent elements if they are the same or not, right? Yeah. Because with this property, you do not need to check non-adjacent elements in an ordered array. You only need to check two adjacent elements in an ordered array. Now, how many comparisons do you need? Only do the adjacent comparison. How many comparisons you need for the worst case? Think about that. How many adjacent pairs can you find in an ordered array? Yeah, because every time you need to do comparison on an adjacent pair, right? But how many different adjacent pairs can you find in this array? Can you see? Anyone? Any of you know that? Tanya? Do you know it? Tanya and Judy? Judy? Andy? Rohan? Any of you? Adjacent pairs, right? Yeah? The first adjacent pairs, okay? The second adjacent pairs, the third, and so on. The last adjacent pair, how many of them? How many of them? Counting problem. And we learn a counting technique, counting by reference. Can you use the counting by reference to get this number? The first pair, can you find some reference number for the first pair? First pair, you can use the subscript of the second element. The second pair, as the reference is the subscript of the last element in the pair, and so on. Yeah. Then the last pair, the subscript of the last element in the pair, right? Yeah. So then you count the number of subscripts, the number of comparisons you need to do, n minus 1, right? N minus 1, counting by reference. Okay? Adjacent pairs, you only compare adjacent pairs. Okay? Not global pairs. Our first algorithm, the brute force, we need to compare the global pairs, right? Yeah. So you can see after the sorting, after we put some investment in data organization, then we can reduce the work from working on global pairs to on adjacent pairs. That's the main difference, main improvement in the second algorithm. Okay, all right, yeah. So here, only need to compare two adjacent elements. Yeah, and here I wrote a pseudocode. Yeah, yeah. So here, to let you see the pseudocode. Yeah, a for loop, so you can do the comparison checking easily. Yeah, yeah. The answer is n-1 comparisons. n-1, that's for the worst case, right? Yeah, that n-1 is the worst case. Worst case. Best case, still one comparison. One comparison, it returns false. Yeah. All right. Yeah. So here, some discussion, some summary after we learn. So here you can see our second algorithm. We need to do the work, two parts. The first part, organize the data by sorting, and we need to pay n log n. The second part, the worst case, n-1 comparisons. Okay, yeah. Next, we will compare if the second one is better or first one is better. Yeah. Second one better, first one is better. Yeah, yeah. All right. So that's the work we will do in the next topic. Yeah. So now here, yeah, next topic, we do that comparison. Yeah. All right. Yeah. But here you can see, at least you can see, yeah. Sometimes when we do some valuable work to organize the data, we can do much better in our processing part. Yeah. So when we do the comparisons, for processing, so we can do much better. Yeah. Yeah. All right. Yeah. So that's this topic. So now I want to move to part B of module 2, continuation. Yeah, so we continue. So we finish the discussion of this solution. Yeah. Oh, yeah. That's always when I touch it. Yeah. So always enlarge. Yeah. Now I want to get out of the presentation. Yeah. Oh, yeah. All right. Then move to part B and then part C. All right. All right. Part B, growth functions. Yeah. B.1, introduce growth functions. Yeah. So this is important concept. Yeah. So our goal, we need to study analysis of algorithm efficiencies. Yeah. In order to prepare you to understand some abstract concept later, so let's understand the growth function concept first. Yeah. All right. Here, at the beginning, so we want to look at the formula between running time and the number of basic operations. Yeah. Running time, yeah, response time or execution time of a program. Yeah. And another, last time we also used another measure, stable measure. We call it stable measure, right? Yeah, stable measure. The stable measure number of basic operations. Yeah, yeah, yeah. Later I will explain this basic operations. Yeah. The running time, this measure unstable. Okay, this measure unstable. Yeah, but second measure stable. Yeah, but these two measures, they are correlated. Yeah. First, let's look at the relationship between these two concepts. Okay. Notations. Yeah. Let us use this t function, capital T of n, as the running time function. And the number of basic operation, we use C of n. C of n, the number of basic operations. Yeah. For different algorithms, the basic operations are different. Okay? Yeah. So here we use this abstract concept, basic operation. Yeah. For example, in our sorting algorithm, sort type problems, the basic operation comparison. Comparison is the basic. So the most commonly used operation in this algorithm, the basic operation. Yeah. If we look at our polynomial evaluation problem, the basic operation is multiplication. Yeah. Because the most dominant operation in that problem, multiplication. Yeah. All right. Here, yeah, this basic operation contributing the most to the total running time. Yeah. So that one we call the basic operation. Yeah. All right. So in order to compare these two concepts here, T of n and C of n, we need to make a small assumption here. The assumption is the execution time of one basic operation here is little c op. Yeah. Little c sub op. In this notation, we use it to represent the amount of execution time for one basic operation. So for one particular computer, so this quantity, this number could be found. Yeah. Yeah. So here we do not need to provide explicit number here. Yeah. So just there is such concept there. Yeah. We use it for our discussion. Yeah. All right. Now let's consider formulas. Compare the formula. And here in our formula comparison, we want to take an approximation approach. Yeah. Not exact. So, yeah. Because many times in our discussion, yeah, it's hard to do exact representation. Yeah. So it's very common we need to do approximate representation. Yeah. All right, so here the approximation comparison is T of n approximately equal to little c op times the number of basic operation, the C function, capital C function. That's the relationship between these two functions, a capital T function and a capital C function. Yeah. Yeah. One small constant connect these two functions. All right. Yeah. And here you can see these two functions, the function values of these two functions are proportional on the same computer. On the same computer. So these two function values are proportional. Yeah. Yeah. All right. Yeah. So here you can see two different measures. One is unstable measure, another is stable measure. Yeah. But their connection, the connection between these two measures on the same computer, yeah, there is a special constant here. Okay, a special constant can explain the detailed connection between these two functions. Yeah. All right. So now, let's do the next discussion. Yeah. Approach. All right. So then, when we do efficiency analysis, yeah. So here, the concept I want to explain. We want to do efficiency analysis. And when we do efficiency analysis, we want to only focus on the major part. Some minor part, not very important, so we may like to ignore the minor factors. We only focus on the major factors. So there is an issue, ignore unnecessary details. A lot of details, but not that important. If it's not that important, we can ignore those details. Because if we can skip those details, we can make our formulas much simpler. Much simpler. Yeah. Yeah. But we have the approximation formulas to the original. The original formulas could be very complicated. Yeah. So we want to do some simplification. Yeah. But after simplification, we want to have good approximate formulas. Good approximate formulas. So that's the main idea. Yeah. All right. The question, can we ignore some constant? Yeah. In our formulas, we may have many different constants. Yeah. The question, we want to see what kind of constant we can ignore in our formulas. So what formulas? Efficiency representation formulas. Because our goal, we want to study the efficiency of the algorithms. Yeah. And after our analysis, we can get efficiency functions. Yeah. So we will find efficiency functions. Yeah. All right. Yeah. Yeah. So the question. Yeah. Can we ignore some minor terms, major terms, minor terms, some terms not that important, some terms very important? Remember, I mentioned a concept before, the dominant term before. Yeah. Remember? Yeah. I mentioned a concept called the dominant term. At that time, one student asked me, what's the meaning of the dominant term? Yeah. So I said, I can delay explanation of that dominant term. Yeah. So here, I need to explain this dominant term. Yeah. All right. Yeah. Yeah. Let's look at the ratio of these two functions in this way. Yeah. When we do the ratio, we compare the same function but with two different problem sizes. One original problem size n, another double the problem size. Okay? The right hand side also original problem size, one function value. Then we look at the function value with doubling the problem size. Okay? Yeah. doubling the problem size, then we take the ratio, two sides. When we do that, you can see this little constant gone. Little c op cancel out. It's gone. It's gone. Okay. Yeah. So we have this approximate equality. It's approximate equality. Okay. Yeah. All right. This new representation can tell us some useful information. So that is the useful information. So when we double the problem size, the ratio of the t function is approximately the same as the ratio of that c function, capital C function. Same ratio. Same ratio. Okay? Yeah. So same increasing ratio. Because when the problem size is larger, the number of basic operations or the execution time in general we used here usually should be larger. So we treat this ratio as the increasing ratio. The values of the functions increasing. Okay? Yeah. All right. Yeah. But the good thing is that this constant is gone. The constant is gone. Yeah. So that means no matter what value this constant takes, these two ratios are the same. So this formula does not rely on that little constant. So you can see, we can use the ratio here to see the increasing rate without knowing the little constant. Right? Yeah. So that means that constant, in some sense, here I say that in some sense, in some sense, it is not that important. So we can ignore. We can ignore. Okay? In some sense. All right. All right. So, because this ratio can tell us how fast it changes. The larger the ratio, the faster the function increases, right? So we can see that in that way. The larger the ratio, the faster that efficiency function increases. In that way. All right. Now we can introduce the growth function concept. So we did the preparation. Now we introduce the growth function concept. All right. What is the major term in the efficiency function? I just mentioned that dominant term before. So this time we need to look at the dominant term and how to simplify the original efficiency function. All right. So the major term, so we mean the dominant term. Dominant term, major. Other terms, minor terms. So, all right. Let me use concrete example here to explain this major term or dominant term concept here. So let's look at the solutions we got before. Selection sort. In the selection sort, what is the efficiency function? The function for the number of comparisons in the selection sort. So recall the efficiency function is 1/2 times n minus 1. All right. Can we expand this formula, multiply out, and get two terms? The first term, 1/2 n squared. Second term, minus 1/2 n. Two terms. Yeah. The first term is the major term, and the first term we can treat it as the dominant term. Yeah. Later, I explain the meaning of the dominant. So what do you mean the dominant term, right? Yeah. Yeah. Let me explain it later. Yeah. All right. So let's look at how dominant is the major term. Yeah. The second term, minor term. How does the first term dominate the second term? We want to see that. Okay, so view the dominant term. Let's do comparisons. Let's do comparison between the first term and the second term. Yeah. And we take the limit. We use the limit function. Yeah. So here we need to use the calculus limit calculation. Let's calculate the limit of the ratio, the first term over the second term. Yeah. After simplification, cancellation, we get a limit of n when n goes to infinity. And you know the answer is infinity. So here you can see where the problem size n becomes very, very large, then the limit of the ratio of the two terms approaches infinity. Approaches infinity. Yeah. Based on this computation result, can you see how the first term dominates the second term? Right? The first term dominates the second term because their ratio approaches to infinity. Right? Yeah? Yeah. If the ratio approaches to infinity, that means the second term comparing with the first term is so small. If we ignore the second term, there is no significant loss, right? No significant loss. Yeah. Yeah. All right. Especially where n is very large. Yeah. When n is small, so that loss could be relatively large, right? Yeah. But in our discussion, our main concern is when the problem size n is very large. Very large. That's our main concern. Okay? Yeah. All right. So now you understand why we call it dominant term. Yeah. All right. Yeah. So then, in this dominant term, there is a leading coefficient 1/2. Leading coefficient 1/2. Still, yeah. Then, if you recall what we did in our previous slide, when we take the ratio t of 2n over t of n, another one, c of 2n over capital C of n, then this ratio is gone, right? The leading coefficient that coefficient is gone. If we take the ratio like this, okay, double the problem size, then take the ratio, then that leading coefficient will be canceled out. So it's gone, okay? Yeah. So it's gone, that means that constant is not that important. It's not that important. In some sense. Yeah. In some sense, not that important. Okay? Yeah. So that means in order to see the increasing trend, it's not necessary to keep this leading coefficient. Okay? So we do another round simplification. Yeah. The first round simplification, we cross out the minor term. The first round simplification. And the second round simplification, we ignore the leading coefficient. Yeah. So we only look at the main part of the function, n squared. And this n squared function, we give it a name, so we call the growth function of this efficiency function, growth function. So that's the meaning of the growth function, that concept. Okay? Yeah. So now you know how to get a growth function of an efficient function. Given an efficient function, you do 2 rounds of simplifications. 2 rounds. The first round, ignore all the minor terms. Only keep the dominant term. The first round simplification. Second round simplification, you simplify your dominant term by ignoring its leading coefficient. Yeah, leading coefficient. Yeah. Replace the leading coefficient by 1. Yeah. Yeah. So after simplification, the leading coefficient becomes 1. Very simple. Yeah. Then, after these 2 rounds simplification, you get the growth function of your efficiency function. Okay? Yeah. So now that's the, the meaning of the concept, growth function. You may ask me why you want to introduce this growth function concept. Growth function concept. Yeah. Because we want to represent we want to discuss the efficiency functions, or we want to characterize, so here, we want to characterize the efficiency functions. Yeah, so here, we want to characterize the efficiency functions using relatively simple functions. Relatively simple functions. Here you can see we do 2 rounds simplifications, so we want to make our growth function as simple as possible, right? Yeah, as simple as possible. And then we use those relatively simple functions to characterize our efficiency functions, put into different categories. N squared category, or n category, or log of n category, different categories. Okay? Yeah. All right. Yeah. So that's the reason we want to introduce this concept. Okay? Yeah. All right. Yeah. Next, B.2, compare growth functions. Yeah. So we want to do comparison, the growth functions. Yeah. All right. So compare 2 growth functions. Yeah. All right. So let's go back to continue the discussion. Yeah. So we haven't finished the discussion of our problem number 5, the element uniqueness problem. In that problem, we use 2 methods, method 1 and method 2, and we haven't compared which one is better, right? Yeah, we want to see which one is better. Okay. In the first method, we just look at the worst case efficiency, this efficiency function. And the second one, there are two parts of work we need to do. The first part, organize the data. We need to use n log n. And the second part, we do local comparison, adjacent comparisons. So we need n minus 1 number of comparisons. Yeah. And these two functions, yeah, which one is better? Yeah. For the first function, yeah, so after we do 2 round simplification, we get n squared. Yeah. Now, how to get the growth function of the second one, the second function? Yeah. Can you see what is the growth function of the second one? Method 2. Yeah. Ignore the minor terms. Only keep the dominant term. Yeah. But make the leading coefficient of the dominant term 1. So what is the growth function of the second one? Can you see that quickly? Yeah. That's n log n. N log n. Oh, not n, yeah, because n is not as large as n log n, right? Yeah, 10, yeah. Because, yeah, we want to keep the largest term. N is not the largest term. N log n is the largest term. Yeah. So, yeah. So, yeah, you will get used to it. Yeah. So we know. Yeah. Later you will quickly, you can identify which term is the largest. Yeah. All right. Next, for the comparison, when we do the comparison, how about we just compare two growth functions, right? We just compare two growth functions. So I leave that comparison part after our break time. Yeah. So let's take a break and come back at about 7.